All right, this is probably the most important chapter in the entire course, and it's going to take us a little bit of time to get through this one. So settle in and try and work through this. Grasping the concepts in this chapter are absolutely critical to success in the course. This is on time value of money. So, time value of money, there's a professor that I had at Notre Dame many years ago, and he said, time has a money value. So as you sell your hours, you expect payment in return. So your time has a money value, certain dollars per hour. And money has a time value, meaning that money today is worth more than the same amount later. And we're going to talk a lot about why that's the case and how to calculate that. But remember that concept that money today is more valuable, all things being equal, than money tomorrow. So for time value of money, the principles and computations used to revalue cash payoffs from different times so that they're stated in dollars of the same period. Essentially, we bring everything back to period zero so that you have an apples to apples comparison as to what the value of those dollars are. So dollar amounts from different time periods should never be compared. Rather, the amount should be compared only when they are stated in dollars at the same point of time or bringing them to their present value. Dollars from different time periods have opportunities to earn different amounts of interest. So different length of time and different return profiles. So here's the conceptual question. At a 10% opportunity cost rate or 10% interest, which is better, receiving $700 today or receiving $935 in 3 years? Now, if I said receiving $700 today or $700 3 years from now, that's a pretty easy answer. You're going to say, hey, every day I want $700 today. But at 10% interest, is it better to get $700 today or $935 in 3 years? So let's take a look. To answer the question, we've got to revalue the cash payoffs so they're stated in the dollars at the same time period. So what we're going to do is, you can see here that there's a timeline, cash flow timeline. And option A, the valuation of A equals $700. And that's at period zero today. You know you have $700 in the bank. And so you can do it one of two ways. You can compare it one of two ways. You could say, okay, if I have $700 in the bank now at period zero, and I've got a rate of return of 10%, I can add the interest and figure out how much that's going to be worth the future value at period 3. Or we know that the other alternative is I have $935 at period 3, so we can take out the interest and figure out how much we would have as a present value today. And I know this is a little bit confusing, but we're going to walk through each one of these. So for cash flow timeline, that's essentially a graphical representation of the cash flow. So we start at period zero where you've got $700, you've got a rate of return of 10, and we say, okay, period 1, period 2, period 3. At period 3, what's the future value? So PV, you'll see very often in this course, it's present value. That's the beginning amount that can be invested. The future value is the value to which an amount invested will grow at the end of N periods. So this, in this case, N would be 3, at an opportunity cost rate equal to R. So in this case, R is 10%. So there's a few types of cash flow patterns. Each one of these has a little different way that they're solved. Fortunately, Excel handles all these extremely well. So we're going to utilize Excel to solve for most of these problems. So you've got a lump sum amount. So that's a single payment. It's either received or made that occurs today or some date in the future. An annuity, which is multiple payments of the same amount over equal time periods. Or you have uneven cash flow, so multiple payments of different amounts over a certain period of time. So in this case, it might be I'll give you $935 3 years from now. This might be I'll give you $300 each year for the next 3 years. And this might be I give you $400 today, I give you $200 in 1 year, I give you $100 in 2 years, and I give you $35 in 3 years. So future value. To compute the future value, we use this miracle called compounding, where essentially we push forward the current amount by adding the interest for each period in which the money can earn interest. And generally that interest compounds on itself. So if you have a 10% interest rate this first year, you have $100, and if it's 10% year one, at the end of year one, you'd have $110. At the end of year two, you wouldn't have $120, you'd have $121 because you're going to get 10% on $110, not just the original 100, because you earn $10 of interest. So it continues to grow, and the interest, you get interest on the interest. So there's a few ways to solve time value of money problems. The first one is you could use the cash flow timeline, which you saw. You could use an equation, you can use a financial calculator, or you can use a spreadsheet. For the purposes of these lectures, we're going to focus on the equations and a cash flow timeline. Most of you will never use, never see, and should never buy a financial calculator. And for doing your work for the class, you should be using either the equations and a regular calculator or a spreadsheet. So let's go back to the problem that we just discussed. So we're looking at future value of $700 invested at 10% per year for the next 3 years. So we start with $700. We have a 10% interest rate. So if we use a cash flow timeline, 700 times 1.10. So 1 plus the interest rate gives us $770. Then again, so that's at the end of year one. At the end of year two, we multiply that amount again by 1 plus the interest rate, so 1.1. That gives us $847 at the end of year two. At the end of year three, or at the end of year three, we go through that same exercise. We multiply our balance at the end of year two by 1.1, which is 1 plus the rate of return, and we get $931.70. It's the future value of $700 invested at 10% per year for 3 years. In the equation solution, cash flow timeline solution could be written as an equation. You can see how this works. You start with $700, and then you have 1.1. So 1 plus the interest rate, and interest rate, 100% interest is 1.00. So it's kind of like a batting average if you're in a baseball. So 10% would be 0.10. And we multiplied it. If you look back here, we multiplied it 3 times. 1, 2, 3. So we would cube it here, 700 times 1.1 cubed. So that's generalized for all intents and purposes, and for basically any use if you've got a steady stream of cash flows. The future value is equal to the present value times 1 plus R, the rate of return, to the n number of periods. So 700 to 1.1 to the 1.1 cubed. So 1.1 cubed, again using your order of operations, that comes to 1.1 times 1.1 times 1.1, which is 1.331. And if you multiply 1.331 times 700, you get $931.70. The same answer as you get back here. In Excel, you're going to set up a table that contains the data used to solve the problem. You're going to click F of X, which is a button, and choose the future value function. And then click the cells containing the data and enter the data into the future value function and calculate your answer. So here's what that looks like. You've got N, number of periods 3, interest rate per year is 10%. Present value in Excel you put in as a negative number. And again, this will make a little bit more sense when we start talking about capital budgeting. But for now, understand that your present value, if you're solving for future value, put the present value in as a negative number. Your payment equals 0. and payment type equals 0, because you're not getting additional payments made throughout the course of the period of time. So it's just one payment of $700 at the beginning, and then it compounds at 10% interest. So what's the future value? And again, there's the format is essentially going to be future value equals future value, and these are your various variables that need to be solved for. And so you can see that when you use the f of x functionality, it'll pull up a wizard to be able to fill this out. But without the wizard, you can see that essentially it's going to look like this. You've got a future value. This is the equation that's actually in this cell. You can see that here in the cell line. Here's the f of x function. You can see that it's $931.70. That's the solved function, and you can see that that's B2, B4, B1, B4, B3, B5 with commas between them, and that's the way the function is set up. You can see that the first thing it looks for the future value is the interest rate per year. Then it looks to the number of periods. Then it looks to the number of payments and the payment type, which is here, and it goes, okay, what's the present value amount? So you can see how that would be written out. Here's the values. Future value at 10% for 3 periods with no additional payments, $700 paid at the beginning, and it's an ordinary annuity. So we'll talk the difference between ordinary annuity and annuity due. If you enter all this in, it will give you that same $931.70. Now, it might seem a little bit more complex to do it through the spreadsheet, but I'm here to tell you that using and learning Excel is going to pay dividends, no pun intended, is going to pay dividends over the course of not only your academic career, but your professional career. So take the time, if you're not comfortable with Excel now, take the time during this course and even after this course to get yourself comfortable enough in Excel where you know how to utilize things like the formula function, that you can do some of the basic formulas and you can handle solving most of your basic setups in Excel. So future value of an annuity. We talked a little bit about what an annuity is. An annuity is a series of equal amounts paid at equal intervals. So that would be like $300 a month for the next 12 months. An ordinary annuity, so we just saw where you can have an ordinary annuity or an annuity due. An ordinary annuity is an annuity where payments occur at the end of each period. An annuity due is an annuity payments that occur at the beginning of each period. So if you have an annuity due and it's $100 a month for the next 3 months, they would pay the $100 on the first of each month. So the first of February, the 1st of March, the 1st of April, for instance. If it's an ordinary annuity, they would pay on the last day of the month. So they would be paid on February 29th, March 31st, and April 30th. So what's the future value of a 3-year ordinary annuity of $400 and 5%? So in this particular case, ordinary annuity, so it's paid at the end. So you can see here's your rate of return, 5%. We're going to get $400 at the end of year 1. We're going to get $400 at the end of year 2. We're going to get $400 at the end of year 3. And each one of these, as what the assumption is that it's going to be, when you get that $400, you're going to deposit it, and that deposit in a savings account or some other instrument, or invest it, and that's going to give you this 5% return. So you take that first $400 that you receive at the end of period 1, and you invest that for 2 periods, 1, 2. And so you've got at 5%, so you've got your 1 plus R, which is 5% for 2 periods N, and that gives you $441. Your second payment you receive at the end of year 2, and you get 5% interest on that for 1 year, so that's $420. And then the third one you receive at the end of year 3, you get 5% interest on that, but it's for 0 periods. You didn't have any jumps from 3 to 4, for instance. And so for that 0 period, anything to the 0 power is equal to 1. So that's 400 times 1 is 400. You just add these together, and the future value of the annuity at the end of year 3 is $1,261. So if you got $400 a month or $400 a year for 3 years of an ordinary annuity and invested at 5%, you'd have $1,261. Here's the equation solution. Future value of an annuity at n periods is equal to the payment amount. And we'll walk through what this looks like for this particular one, but this is your general equation. And then you multiply the payment amount, in that last case was $400, times 1 plus R, the return. So in that case was 1.05 to the n minus 1. So again, if you go back here, 400 times 1.05 n minus 1 plus same rate of return n minus 2, etc., to 1 plus R till this gets to 0. So again, this is why math is a prerequisite. This is a summation. So it essentially is the Greek letter sigma, and it counts for all of what's happening up here in these brackets. So you essentially cycle through each time. You start with n minus 1. So in the last case was 3, so you start with a 2 here. And then each time you go through it, this decreases. So you go 2, 1, and then it stops at 0. 1 plus R to the t. So again, the payment can be reduced to 1 plus R to the, in this case, 3 minus 1 over R. So this is the ultimately reduced formula for future value of an annuity. So let's take a look at the last problem. We have $400, 1.05 cubed minus 1 over 0.05. So that, if we do the brackets first and do our order of operations, we end up with 3.1525 by taking that 1.05 to the cubed minus 1 over R. Multiply 400 by 3.1525, and we get 1261. For the future value of an annuity due, you get the payment at the beginning. And so the difference, and you can see what that difference is, if you get the payment at the beginning, you actually add one more compounding period to each one of these. So where before you basically only did this, 1.05, 2, 1.051, 1.050. In this particular case, you add an additional compounding period. So you'd follow the same exercise, except you'd end up with $1,324.05. Payments are made at the beginning of the year, which means that each payment earns one additional year's worth of 5% interest. So here's the equation solution. Essentially, it reduces down to 1 plus R, rate of return, to the n periods minus 1 over R times 1 plus R. So if we look at it from the last problem, you remember that we had 400 times 1.05 cubed minus 1 over 0.05 times 1.05. So we'd gotten 3.1525 from the last one times 1.05. So again, order of operations says we do this first. So we get 3.310125 times 400, which was the amount of the payment, which gives us $1,324.05. So a couple definitions. PMT is a constant cash flow. That's an annuity stream. So if it's a payment, it assumes it's a constant cash flow. Cash flow is CF. You'll see that used throughout the book and throughout these the notes and in practice. Cash flows in general, it's both constant cash flows like annuities and uneven cash flows. And we're going to see quite a few uneven cash flows when we get to capital budgeting. So find the future value of an uneven cash flow stream. So in this particular case, we've got an R of 5, we've got 3 periods, but we have $400 paid at the end of year 1, $300 paid at the end of year 2, $250 paid at the end of year 3. Again, it's easy to see how this would work using the number or using a cash flow timeline, because you got $400 at the end of year 1 at a 5% return. So you do just like you did on the last one. Multiply that out, and that becomes 1.05 with 2 compounding periods, 1, 2. So that's $441. $300 comes in. You've got 1 compounding period, so that's 300 times 1.05, and that goes here. $250 comes in the last day of year 3. That's got 0 compounding periods, and so that becomes $250. You just add these together, and it's $1,006. Here's the equation for the future value of a cash flow stream. Again, remembering that this sigma is summation, and you cycle through from the number of periods n until you get to period 1. You have your cash flow amount multiplied by 1 plus r to the n minus t. And you can see that that's just what we're doing here over and over and over again. Each time you go through it, you subtract 1 off of n, and it just cycles back down through, and you feed that through. But this is the equation methodology. So again, you go through 400 times 1.05 to the second, plus 300 times 1.05 to the first, plus 250 times 1.05 to the 0. Just multiply each one of those out. You use your order of operations and add things together, and you get 1,006. So for present value, so that's us taking all the things from today and taking it out to a common future value point. In this case was period 3. Present value is taking the value today of a series of future cash flows. So there's an estimate of expected future cash flows, and then we discount those, and that's the process of finding the present value, the amount that you'd be willing to pay for that cash flow stream today if you had a choice where you would be indifferent. Finding the present value is reverse of finding the future value. So interest is taken out of the future value to determine a present value. So present value of a lump sum amount, this discounting to compute the present value of an amount, we bring back the present value by taking out the interest for each period in which the money can earn interest in the future. So again, going back to the original problem, we start at year 3 with $935, and we say, okay, we've got to take the interest out. So that's 1 over 1.1. So we're taking that interest out. That meant we had $850 at the end of period 2. We take that 10% out that it earned. So that means we had $772.73 at the end of period 1. We take that 10% out, and that means we had $702.48 at period 0. So the present value of $935 in 3 years at 10% is $702.48. And here's the equation solution. The present value is equal to the future value divided by 1 plus r to the n, where n is the number of periods, and this is the future value of period n. So future value in that case at period 3 was $935 divided by 1 plus r, in this case 10%, the n, which in that case would be 3, and that will give you the present value. So $935 times 1 over 1.1 to the third. So that's order of operations says you do this first, then you divide 1 by that amount, which gives you 0.751314801. Times 935 is 702.48. Present value of an ordinary annuity is essentially the present value of an annuity with n payments, each made at the end of the period. Each payment is discounted, and the sum of the discounted payments is the present value of the annuity. So again, just like we went through, it's just doing the other thing, the future value backwards. So you had a payment at the end of period 3 that was $400, and it was a 5% interest rate. So we take 1 over 1 plus 0.05, the interest rate cubed, because you have 1, 2, 3, and you bring that back, and that's $345.54. The second annuity was paid at the end of year 2, and so you had 1 compounding period this way and 2 going back that way. So you use 2 since you're headed this way. 1 over 1.05 and to the second. And then same thing, 400, 1 over 1.05 to the first to bring it back to period 0. So you have $345 is the present value for the payment in period 3. $362.81 is the present value for the period at the end, or the payment at the end of period 2. And $890.95 is the present value for the payment at the end of period 1. You add those together, and the present value of that annuity is $1,089.30. The equation solution for this, if you go through the entire process, it boils down to this. You take the payment amount and multiply it by 1 minus 1 over 1 plus the rate of return raised to the number of periods over the rate of return. So in that last particular case, here's how it looks. You had a $400 payment, you had a 5% interest rate, and you had 3 periods. And those tend to be the same 3 variables in any time value of money problem is going to be how much am I getting paid, what's the interest rate, and how many periods. So you just work through it as a math problem once you get it in the formula and you go, okay, order of operations says I do my exponents first. Then I divide that into the -1. Then I subtract 1 from it. Then I divide it by 0.05. That gives me 2.723248. Multiply that by 100 because you do everything that's in brackets first, and that gives me $1,089.30. If you have a present value of an annuity due, that's where the payment's made at the beginning of the period. So again, just like when we did the future value of an annuity due, this is going in reverse. And so you multiply everything by that extra period. So you have the 400 that was paid at the end or at the beginning of period 3 or period 2, so that you discount back, and you have 5% taken out of each payment, so that's $362.81. You go through the same exercise here, $380.95, and the same one here, $400. You add those together, and the present value of an annuity due is $1,143.76 for a payment of $400 made at the beginning of each period at 5% interest for the 3-year period. And just like with the present value of an annuity, the present value of an annuity due has the same formula. This is all the same, except you multiply it inside the curly brackets by 1 plus R, where R is a rate of return. So as you go through it, we went through this before, you start with your order of operations. So you go with your cubing your 1.05 first, divide that, divide 1 by that amount, subtract 1 from it, divide 0.05 into that, multiply that by 1.05. So now you get 2.723248 times 1.05 times 400. That gives you $1,143.76. Sometimes you have perpetuities. Perpetuities are payments that are made forever. And so you've got perpetual annuities. So that's where we go perpetuities. And so a perpetuity is a perpetual annuity. It's essentially the same amount is being paid every period forever. And part of the concept of time value of money is worth more the sooner you get it. And so if you go out, way out, if I say what's the value of $100 to you in 40 years, it's not that high. You're going, I might not even be alive in 40 years. I don't know what the interest rates are going to be. I don't know what $100 is going to buy me. I don't know what inflation is going to look like. So present value of, $100 40 years from now is relatively low. And so you've got the present value of a perpetuity is a very simple calculation. It's essentially the payment times 1 over R. And so that could even be further reduced by it's the payment, the amount that you're getting paid every period over the rate of return. So in this particular case, the present value of a perpetuity of $100 a year, where the rate of return is 5%, the value of that perpetuity is $2,000. So in theory, you would be willing to give $2,000 today for the right to receive $100 forever if your required rate of return was 5%. Present value of a perpetuity, if your required rate of return is 10%, would be $1,000. And so again, this shows a fundamental principle in finance. Everything else being equal, so the payment being equal and the amount of time being equal, in this case infinity, the higher the rate of return, 10% required versus 5% required, the lower the value of the investment. And you can see that clearly here. So for present value of an uneven stream of cash flows, so present value of an uneven stream, it's the same thing as we did with future value. Again, the same concepts, just going the other direction. So we saw that same calculus where we've said, okay, in the third period, we had $250 paid to us. We discount that back 3 times, 1, 2, 3. So you can see that N equals 3 here. 5% required rate of return. So that is worth $215.96 today. $250 3 years from now, 5%. For period 2, we received $300. If we discount that back 2 periods, that's worth $272.11 today at 5%. And if we receive $400 a year from now, we discount that bank 1 spot, and so that's discounted back 1 period. So $400 a year from now, 5%, is worth $380.95 today. So you add these together, and so you would be willing, if your required rate of return is 5%, you would be indifferent if you got $869.02 today, or if you got $400 a year from now, $300 2 years from now, and $250 3 years from now. So the sum total of this is $950, and for the $950 getting paid over 3 years, you would be indifferent if you had a 5% required rate of return to receive either that $950 paid out that way or $869.02 paid today. The equation, again, very similar to the future value equation. You've got your summation, you cycle through it, and just like we did with that number line, and you have your cash flow for the period T, and then you have 1 over 1 plus required rate of return to the T. And that's essentially this value here. And here you can see it solved. So 250, 1 over 1.05 to the third plus 300, 1.05 to the second plus 1 over 1.05 times 400. That's the multiplication. You could do that on your calculator or on your computer. You add those together and you get $869.02. So a couple things to keep in mind, and I use some of these terms interchangeably, and they're probably not correct to use interchangeably. Future value contains interest. Present value does not. And so when you're calculating a future value, you're adding interest in. Present value, you're taking interest out. An opportunity cost rate of 10% A lump sum payment of $700 today is the same as a lump sum payment of $931.70 in 3 years. And we saw that, we just calculated that a couple different ways. The present value of 700 has no interest, right? That's today's money, $700. The future value of $931.70 contains 3 years of interest, and that 3 years of interest is $231.70. The difference between the $700 that you had in period 0 today and the $231.70 you would have at the end of the 3-year period. And you can see that here. So we start off 10% required rate of return. There is no interest at the end of, we're at period 0. So present value of period 0 is 700. Present value at period 0 is always going to be 700, but we add the interest. So in the first period, you get 10% interest. So you go, okay, here's the $70. You can see that here. The second period, you get 10% interest on $770, which is $77. And you can add that here. So you add the present value, 700, plus the interest from year 1, plus the interest from year 2, 147. So now you have $847. Then you go to period 3. And you go, okay, I now get 10% interest on $847, which is $84.70. And so you started with 700 from here. You got $70 of interest. You got $77 of more interest. Then you've got $84.70 more interest. So that's $231.70. So at the end of the period of time, if you think about this as a bank account and you deposited $700 in your bank account today, a year from now, you had $770 and you didn't take any money out. 2 years from now, you'd have $847 in your bank account. And 3 years from now, you'd have $931.70 in your bank account. You'd have the interest from year 1, the interest from year 2, the interest from year 3, plus the original investment. So that gets you to $931.70. Generally, for the class, you have annual compounding. However, there's other compounding periods. You can have semi-annual, quarterly, monthly, compounded continuously, compounded daily. And so essentially you have to, if you do that for any of those periods, you have to increase the number of periods and you decrease the corresponding interest rate to the corresponding daily rate, quarterly rate, semi-annual rate, monthly rate, and we'll walk through some of those. So the future value of a lump sum is larger if interest is compounded more often, holding the stated rate or holding the stated rate constant. Why? So if compounding is more frequent than once a year, for example, semi-annually, quarterly, daily, continuously, interest is earned on interest, which we just saw on the annual compounding. And so it compounds more often. So compared to annual compounding, a greater amount of interest is earned when compounded more than once a year. So here's an example. You've got a simple rate of interest, which is the quoted rate, and that's used to compute the interest paid per period. So they may say, we're paying 10% compounded daily, or 12% compounded monthly. The annual percentage rate is equal to the simple rate. The effective annual rate is the actual annual rate of interest actually being earned. And we're going to take a look and see how to calculate this. So again, kind of giving the definitions again. Simple rate is a simpler quoted rate. It's not really used in calculations per se. The periodic rate is a rate per period, per year, per month, used in calculations. So that's going to be the periodic rate of interest. And then you've got the effective annual rate, which is used to compare returns on investments with different interest compounding periods. Generally, the simple interest rate is stated in a contract, and the number of interest periods per year is given. So here's a couple examples. You've got 9% compounded quarterly and 9% compounded daily. Now, coming back, given what we've just talked about, which do you think is going to pay you more money over the course of 1 year, 9% compounded quarterly or 9% compounded daily? The answer is 9% compounded daily. The more frequently, if the simple rate of interest is equal, the more frequently it compounds, the higher the value of the underlying investment. So for your periodic rate, that's going to equal your simple rate divided by M, where M is the number of compounding periods. So for those two examples that we just talked through, 9% compounded quarterly, M is 4, so 9% is the simple rate, compounded quarterly, so that's 4 times a year, and the periodic rate is going to be 2.25% per quarter. 9% divided by 4. 9% compounded monthly, number of periods is 12. So you have 12 months in a year. So you're going to divide 9% by 12, and you're going to come up with 0.75% per period. So the effective annual rate is the rate that causes a present value to grow to the same future value as it would with multi-period compounding. So again, it's essentially trying to bring everything into an apples to apples comparison. And this is another relatively straightforward formula. But again, we're back into exponents and such. So you've got 1 plus your periodic rate. So if we were looking at the last one and it was a monthly compounding, you say 1 plus 0.075, so 75 basis points or 0.75% to the 12th minus 1. So you can see that calculated out here. The effective annual rate is the simple rate over M raised to the M power minus 1. So 1 plus 12% over 12 to the 12th power. So in this particular case, minus 1. So in this particular case, if you have 1.01 to the 12th minus 1, that's 12.68%. So where the simple rate is 12%, the effective annual rate is 12.68%. So by compounding more frequently than once a year, you're picking up an additional 0.68% of interest on that investment. So amortized loans are loans that are paid over the course of its life, normally equal monthly payments. And that's almost all of us who have house payments, car payments, student loan payments. Those are amortized loans. So that's you borrow X amount of money at the beginning of a period and you have the same payment for 5 years, 60 months, however your car payment might be, 120 months for a student loan, 360 months for a house. So an amortized loan is a loan that's paid in equal repayments over the course of its life. A portion of the payment represents a payment of interest, and the remainder is a repayment of the amount that was borrowed or a decrease in principal. Amortization schedules show how much of each payment represents principal and how much represents interest. So here's a amortization schedule. We're going to build a quick one for a $33,000 loan at 6.5%. That requires 3 equal payments. So what does that look like? So at the beginning, you have the beginning balance of the loan is $33,000, and you're going, okay, you're essentially solving for this number. What's the payment amount need to be in order to be able to get this to 0 at the end? And we'll walk through separately an Excel formula to be able to do that. So you essentially start off with 33,000, and you can build this out in Excel as well. You take 33,000, you're going to solve for this. You say interest at 6.5% is equal to, so this amount is equal to 1 times 0.065, which is $2,145. And then you've got this amount is your equal payment. So this minus this is equal to $10,315. That gets you a remaining balance of $22,685. That now flows down to year 2. You've got another payment of $12,460. You figure out how much was the interest. So $1,474.53, which is this times 0.65. You subtract this from this, and you get $10,985.48, which leaves you with $11,699.53. You bring that down. Then you've got another payment of $12,460. You said, well, wait a second, I only owed $11,699.53. Well, you still have to pay the interest. And so the interest on $11,699.53, 6.5%, is $760.47. And so if you take $760.47 and add it to $11,699.53, you get $12,460. So you take $12,460, subtract out the $760.47 of interest. That leaves you with a repayment principal of $11,699.53, which gives you an ending balance of $0. Like I said, I'll put a video up on how to build one of these in Excel, but essentially when you have an amortization schedule, the important thing to remember is you have equal payments in each period. A portion of the payment is interest, a portion of the payment is principal. Principal goes down every year until you eventually reach zero. I recognize that this is probably one of the harder chapters, and it's, like I mentioned at the beginning, the most important chapter in the book, the most important chapter in the class. So if you have any questions on this, and I know it's early in the semester, if you have any questions on this, please post it up to Moodle. Let's have a discussion. Let's work through problems. This is classic math problem stuff, so it's going to be practice and practice and practice until you get the concepts. And once you get the concepts, if you can master chapter 4, the rest of the class becomes pretty straightforward.